Hi everyone. In today's video, we are going to look at three words that we often use interchangeably, meaning we use them the same way, but in fact they mean different things. And so we're going to try to sort out the difference between temperature, thermal energy, and heat. Should you need me, my email address is on the screen. It's rcrawford@jcpsmail.org. Hey, let's hop right in. So first off, when we talk about temperature, generally speaking, we all think of a measure of how hot or how cold something that is. We think of measuring it with a thermometer, whether we imagine that as Celsius or Fahrenheit. Um, but I don't know that that really gets us by in science. So, really, when we talk about temperature, we need to think of temperature as being a measure of the average kinetic energy, meaning motion, of the particles in an object. So, the key word here, guys, is average. Obviously, it's a measurement. We know we're talking about moving particles, but average, that's the key word. Let's make sure that we understand what's going on here. Let's suppose that we take four grades from your science class. Let's suppose you had a 50, a 75, a 100, and a 50. If we add all those together, that gives us a total, right? So the total of those three would be 275. But remember, with temperature, we're talking about the average kinetic energy. So to find the average, we would count how many there were, right? So we had four grades. We'd divide by four, and our average would be 68.75. So you can see that the average is much smaller in this case, obviously, than the total, okay? But when we think about temperature, we're talking about the average motion. It means, generally speaking, what are most of the particles in this object doing? So that's temperature. Let's compare that to thermal energy. Well, when we look at thermal energy is a measure of the total kinetic energy. So notice that how similar these two things are. So this is still a measurement, but it's a measure of the total. So instead of us having that average, after we add everything together and we have that total, that tells us the kinetic energy. Now, this may seem like a really small thing, but it plays out in very big ways. I do want to mention, though, that thermal energy does depend on two things. It does depend on the temperature of the object. So if this object is, 78 degrees Fahrenheit, that is absolutely going to make a difference. But here's the second part, and this is the one that's tricky. Thermal energy also depends on the number of particles that the object is made from. So some matter and some objects are made from fewer particles. Some are made with less particles. In some ways, we can almost equate that to size. So often, this means that objects with more particles, i.e., bigger objects, are going to have more thermal energy. Here's what I would say. So now keep this definition in mind: average versus total kinetic energy. Okay, um, and here's what I want us to do. I want us to decide which one of these two has more thermal energy. Is it this very cold, icy pond, or is it this very hot pot of boiling water? Now, mostly, I think I think that many of you are going to think, "Oh, it's definitely got to be that hot pot of water." Well, this is why thermal energy and temperature can be tricky. Remember, thermal energy is a total. If we look at the number of particles um, inside of this icy pond, then there are a lot more particles. And remember, if we were to add those tiny motions of all those particles together, right? So if we were to take and add the tiny motions, the total would be much, much greater than the number we're going to get for the average, which is the temperature. Now, clearly, it is true that the pot of boiling water has a higher temperature, but something that is much larger, that is made from many more particles, is often going to have a lot of thermal energy, even though the amount of thermal energy for each particle may be very tiny. When you add up all those tiny motions for all those particles, it turns out to be quite a bit of thermal energy. So, yes, the icy pond, because it is bigger, it has more particles, is going to have way more thermal energy than this pot of boiling water, which only has a higher temperature. Now, how do those two things compare to heat? So first off, please remember that temperature and thermal energy are both going to be measurements. Okay, one is a measurement of the average, another is a measurement of the total. When we look at heat, and heat is much different. Heat is more like an action. It's something that happens. Heat is really just the flow of thermal energy from one area to another. And thermal energy always flows from warmer to cooler, from hotter to colder. So if we have no difference in temperature, then there's not going to be any flow and there's not any heat. Now, even in this class, I have used the terms thermal energy and heat interchangeably. I will not do that in the future, mostly because now you understand the difference. So remember, heat is the flow of thermal energy. So let's take a look at this example. So here we have cube A and cube B. Cube A is going to be much warmer. That's why it's red than cube B. So let's suppose that I like push these two cubes together or move them very closer together. When I put A and B together, thermal energy is going to begin to flow out of this warmer cube. Remember, always flows from warmer to cooler into this cooler cube. And that's going to happen. Thermal energy or heat is going to flow until those blocks have the same temperature. And then after the blocks have the same temperature, they have the same amount of thermal energy, the heat flow is going to stop. So heat is an action verb. It's something that is happening. It is not a measurement. Heat is the flow of thermal energy, and thermal energy always flows from warmer to cooler, never the opposite way around. Okay? Um, when we talk about heat moving between particles, I do at least want to I want to have you think about this example. So let's suppose that this is a piece of metal and we begin heating one end. These particles that are here very close to the heat source, this flame, are going to get heated up first, right? And they're going to begin to move much faster, and they're going to start moving farther apart. But more importantly, as they are moving farther apart, they're going to start colliding with their neighbors. During that collision, that is what's going to pass that thermal energy on down the line. It's kind of like an old bucket brigade. It's this atom is passing to this atom is passing. So this energy actually gets passed and it flows through the object by these collisions between atoms. Okay. Thermal energy, I do want you to know, and heat is moving around us all the time. If you think about our everyday life, we always have examples where things are getting warmer or things are getting cooler. I know that this is a continual battle. I fight with my coffee every day. But let's look at let's look at this example with some hot cocoa. So we've just made a nice cup of hot cocoa and it's really hot. Now most of you understand that over time the heat, excuse me, the thermal energy is going to flow out of this, right? Our hot cocoa is going to get cooler the longer we wait. So why is that happening? Well, you've got thermal energy from the cocoa that moves into the spoon, right? So the spoon is going to get warmer. Thermal energy is going to move out of the hot cocoa into the mug or into the glass. And so that's going to make the glass warmer. And some of it is even going to make its way out into the air that's around it. This is exactly why this heat, this flow of heat, is why our cocoa gets cold over time, because it's giving some of its thermal energy to the things that surround it. Now, this one is a little bit different, even though we're still talking about a drink. Really, here we're trying to make something cooler. So thermal energy here is going to be, we put ice cubes in our soda, and thermal energy is actually going to be moving into the ice cubes. So, you know, the coolest thing that we have is the ice cubes. So energy from the soda itself is going to flow into the ice cubes, which in effect makes our soda cooler. Now, of course, this is also going to make our glass cooler, and the ice is going to get warmer. So in this example, the soda and the glass are getting cooler because remember, thermal energy always flows from warm to cooler areas, and the ice itself is going to get warmer and eventually melt. Okay? So at the same time that this thermal energy is moving into the soda, we're also going to have we're also going to have some heat moving in from the warmer air, and that's why eventually your soda is going to get warm again after all that ice is melted. Here's my last example. So if we look at thermal energy once again, and we can look at maybe some of you have a cat or a dog, and they love to find the warm spot, right? And so if you've ever sat down on to a cushion and then your pet like immediately gets up to steal the warm spot, this is a good example of heat moving from an area, from something that is warmer to something that is cooler. All of these are examples. Guys, that's really going to do it for today. We're going to talk about three ways that heat moves, three types of heat transfers in the next video. I hope you guys have a great day.